All right, so for today, we're going to be looking at how do you organize programs in a way that makes them easier to read, easier to reuse, and other things like that. Okay, so and we're going to use this same program that we were working on last time as an example. Okay, so what we've got here is this program where you enter, your midterm and your final exam grades and your homeworks, and then if you remember now, it's computing the median of the homework, and then it's using that to compute the final grade. Okay. And on the one hand, this program is small enough that you can kind of read through it fairly quickly and understand what it's doing. But you could imagine if you had to write an even bigger, a bigger program, maybe that's 5 or 10 times this size, if it was all just one main function with just all these instructions, boom, 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 one after the next, it's going to start taking longer and longer to understand what's going on here. And then if maybe you had a few programs to write, not just one, but a few, but they needed to use certain pieces that were common, then it's like, well, how do you do that? How do you, instead of just copying and pasting, for example, computing the median of something, you could imagine is something you might want to do over and over again in different programs. Okay, and here, computing the median, well, it's something like these, 7 lines of code compute the median, right? But I had to sort of stare at the code to figure out that it was those 7 lines, and you might like to separate those 7 lines out into something else, into a function. So we're going to be mostly looking at how do we separate out pieces of code into functions. All right, so let's go over here for a second. Got a certain ordering that I want to look at. Okay, so that's one chunk, is the median. What are some of the other chunks of functionality that might be things that you could reuse, or that just sort of constitute a nice chunk of work that you can give a name to? Or here's another thing to think about. Suppose, right now this program just processes one student's homework. If we wanted to expand this to processing lots of students, what kind of things would we end up needing to do over and over again?
Probably inputting the grades.
Inputting the grades, right? So these homeworks, right? So we're going to want to do, this part over and over again, right? Well, and also the beginning part as well. And then at the bottom here, this part about computing the grade, we're going to want to do that over and over again. And the fact that I can say, oh, this is computing the grade, that's almost a nice function name, right? And if you just stare at this like, oh, there's a bunch of multiplications and additions happening, if you're trying to read this program for the first time, you might not realize that, oh, that's computing course grade, the course grade, right? But if you give it a name, put it in a function, now it's going to be easier to read. So let's go ahead and start doing this. Now, what we're going to be doing is what people call refactoring a program. So the output of the program isn't going to, or any of the behavior of the program is not going to change at all. Okay? And what we're going to do is we're going to do this step by step. So we're going to make one change, and then we're going to be able to rerun the program. And then we're going to make another change, and we're going to be able to rerun the program. And the whole point of that is that whenever you make changes to your program, you might introduce errors, bugs. Okay? And if you introduce bugs, it's a lot easier to fix them if you kind of know where they could possibly be, right? And so if you just made one little change and then rerun your program and now it stops working, guess what? That one little change is what caused the problem, right? Whereas if you make a whole series of changes and then you rerun your program and it's broken, you're like, well, of these 10 different things that I just did, what caused the problem? You have no idea, right? So then all of a sudden now you've got this, now you're, stepping through your program and going through this arduous process of finding the bug. Okay? So let's just do one change to begin with. How about we do the reading in of the homework as a function? Okay. So we're going to put that up here. Read homework will be the name of the function. I haven't yet decided what are the parameters or what's the return type. We'll put those in as we figure them out. But the first thing I'm going to do is I'm going to cut and paste this part of the code in. Okay. And then here I'm going to put in a call to read homework. Now, what I've written so far is sort of broken. If I were to try to recompile right now, we get all kinds of problems, right? But this is the main gist of what we want to do. So now, what do we need to really do to make this work? You see any problems with what we've got so far? A little hard to get it all on the same screen here, but I can. Do we have any issues with variables? That's one of the main things you want to look at when you move code around is, are there variables that no longer have declarations to go with them, to go with their uses? So
final are defined up where you use read homework.
So midterm and final are defined down here.
Right.
Are they used inside of here? No, so that's okay, right? But let's look sort of the other direction. Here's homework being defined in here, but it's being used outside of read homework. So that's no good. This variable homework down here is going to say, it can't see into some other function. So it's going to be like, oh, this is an undefined reference, okay? So really what needs to happen is this homework guy here needs to live out here, and then we need to pass it in as a parameter. Now there's lots of different ways of passing things in as parameters, okay? Well, there's at least 3. We can pass by value, which means doing a copy. We can pass by reference, or we can pass by const reference. Of course, we need the type of it in here. But which of those 3 things should we do in this case? The main question is are we just, if we want to pass by value and do a copy, that would imply that we only need to read information out of this thing, and we don't need to change it. Okay? If we're doing it by const reference, the same is true. We're just reading out of it. Okay? But if we need to change things in it and have those changes reflected at the call site, then we need to pass by reference. Okay? So what do you guys think for this one?
Reference?
By reference, that's right. So I'll put an ampersand there to say pass by reference. Okay? Now, here's another thing we need to worry about. Is this, let's think a little bit about the return value of this function. And also, let's think about this return statement here. Okay? that return statement used to be in the main function, and it was exiting the main, which meant that it would exit our entire program. Now that it's inside of read homework, it's sort of doing the wrong thing. It causes read homework to end, but it doesn't end the entire program. So there's something sort of wrong with that. Okay. So there's different ways to deal with this. We sort of need to signal to the caller of read homework that something went wrong. Okay. One of the ways to do that is with a return code. Okay, that's probably the most basic way of doing that. So let me show you what that would look like. You might, probably the most common way to do that is to use a Boolean, or a Boolean flag, or an integer. This is sort of archaic, but people might say use 0 to mean sort of false. Would be one way to do it, or you might choose that like some other number like -1, and that would be sort of in line with if you're exiting the program and the -1 says the program's in error. So you might stick to that convention. Perhaps an even better approach. Well, there's arguments about this, but another approach to think about is to raise an exception. Oops, sorry, that was Java syntax. Okay. Here I'm throwing sort of just a generic exception. Actually, maybe a slightly better one would be, there's a whole bunch of different exception classes. One of them is called domain error. Let me see what. And then the nice thing about exceptions, one of the nice things is you can include, when you construct them, you can include a string that describes sort of what went wrong. Okay. And so now, one thing that's kind of interesting about this is that we can get rid of this message that was printed out at that point, because the caller of read homework might want to do different things. They might not want you to print out to the standard output. They might want instead to throw up a dialog box or something if you're in a user interface. So now what we're doing is by throwing, the person that's calling read homework can catch that and do different things if they want to. Okay. So at this point, we don't really need to return anything from this function. We could just say void. So here you've seen a throw of an exception. What that does is it propagates control, if you're executing step by step. Now all of a sudden it's going to pop back, and it's going to keep popping until either one, it hits a try clause, which we're about to write, or it just pops all the way out of the program entirely, and then it aborts the program. So as it is, this would cause the whole program to abort. But what we could do instead here is we can put a try clause around this. Let's see where did I put this try clause? Over here. So what's going to happen is I want to sort of enclose in this try all the things that sort of depend on read homework working. Okay. So I can go ahead and basically put the rest of this in a try. Now we need to indent all this. Put a catch down here. I'll make this a const reference. so what happens is, let's say inside of read homework, it throws that exception, right? That throw happens. It'll then jump all the way down to this catch, and the exception object that we created in that throw will land and be bound to this D variable here. Okay, and then at this point we can do whatever we want with it. And one, natural thing to do is to just print out what went wrong. Okay, and the what method gives you access to the string that we passed into the exception object. Okay. So you'll see exceptions quite a bit when you're dealing with library functions or other kinds of functions, and you want to signal that something's gone wrong. You don't necessarily know how to deal with the error inside of read homework. Again, whether it should be printed to standard out or a dialog box or something like that. And so you throwing an exception is sort of a way to pass the buck up the sort of chain of command. Okay. All right. So with that, we've got our read homework. It now takes a parameter, and at this point, I'm thinking that this should work. So let's go ahead and try to compile. We have a problem here. Function domain error could not be resolved. So that means it's like, where's this domain error coming from, right? So this is supposed to be coming from the standard library. And if you were to go do some Googling around or looking at a good reference manual, you'd find out that it comes from this standard header called std accept. Okay. Try again. And it looks like we're good. So let's try to run this guy. All right, so now we've made our incremental change to the program. Now we're going to make sure that it still does what we think it does. So entering the midterm and final grade. Okay, now I'm going to enter the homework grades. That X is just to tell it to stop reading in grades. It gets an error at that point. cin will sort of signal that it's in an error state, and that'll cause us to stop. Right? That'll kick us out of this while loop. If you remember a couple times ago, the more normal way to tell it to stop is to hit Control D, but this Eclipse is buggy and goes into a infinite loop when we do that. So, and indeed, it gives us the right answer with 96. So we haven't broken it, and we've made the code a little bit more readable now. Someone reading through this main function will say, like, okay, good. The first step is to read the homework. Okay. How about the next step? Well, let's take this piece out now. So this is computing the median, right? So let's go ahead and create a function to do that. Oh, by the way, you'll notice I'm using a certain style here for function names in terms of like capitalization and underscores. There's all kinds of wonderful religious wars about how to do this. You'll have heard of something called camel case, which is one popular way of doing it, where every word starts with a capital letter. So, like in camel case, we'd instead do it this way. We might call it compute median, or so you might see those options. Those are perfectly fine. I tend to prefer this case of all lowercase with underscores instead. And this is a little bit more common to the C++ standard library, but it's But in sort of the world of object-oriented programming, I'd say the camel case is more common. So if you're looking at Java code and whatnot. So it's just a matter of taste. Different organizations will have different conventions that they like to go with. But in any event, that's just because the standard library tends to go with this style. That's what I would go with as well. All right, so let's again take this code. All right, so that's all the part that has to do with computing the median. Paste that in there. And then and now we need to figure out, go through the same process as last time and focusing in on the variables. So are there variables, inside this function that need, that sort of no longer refer to something? They're sort of dangling variable references. Because, if there's like, for example, this homework variable down here in main is not visible in this other function, right? You have to pass it as a parameter. So that would be one of the things that we need to pass in. And again, we have three choices here. We can pass by value, by reference, or const reference. What would be the right choice here?
By value, since you're not reading, or since you're only reading from it?
Good. That's so in some sense what you're saying is, well, we don't want to do reference because we're not changing the homework vector this time around. We're only reading from it. So we definitely don't want reference. Now, our two remaining choices are either by value to copy or by reference. Now here the choice, either way will give you the right answer. The program will sort of act the way you want it to. However, by const reference is a little bit better in this case because vectors can sometimes get kind of big. Now in this case we know that it's really not that big, but in general you want to keep in your head that in general the inputs to your program might get larger and larger, and you want to think about scalability a little bit, and so you want to think about, well, how expensive is a particular operation like passing this homework vector in with respect to the size of the input to your program. And in this case, if the size of the inputs got very large, the cost of copying would also be very large. Okay, so it'd be linear. It is linear. So here, if instead we do by const reference, now the cost, there's no copy happening. So the cost is always constant time. It's just passing a pointer to the vector. And a reference to it and not doing a copy. So const reference is the right way to go there. Okay. Now is there anything, looking down, so now we need to go, let me go ahead and put that in. Is there anything else, are there any other variables that sort of need work here? Are there variables that are being, maybe defined or assigned to inside of compute median that we then use later on, but now the sort of the link up is broken? So we've computed this median. But what did we do with the median? Right, so declaring median here, we assign to it here. Right, so recall this median guy, it's living on the call stack, the procedure call stack, right? When we exit compute median, that call stack goes away and it's gone. So we've sort of thrown away what we just computed, right? So instead, we need to somehow, well, really, we need to be able to return this result, right? So we could have also, instead of returning median, we could pass median in by reference. That would be another way to do it. But since it's just this one thing, it's a little bit more natural to, and it's not like we never need to read from it, we're only writing to it. In this case, it's more natural to return it. Though this is returning by value, so it's copying. But copying a double is not a big deal. It's always a constant time thing. So returning that. And then now we need to be able to catch that value coming out and assign it to something. So we need to do that. And we also need to make sure that this value median is in fact declared. Perhaps the easiest way to do that is to go ahead and turn that into a declaration with an initialization together. In sort of old school C programs, you'll never see this kind of thing where you've got an declaration and initialization in the middle of the program. That wasn't allowed way back when, and so they would have had to put like, right at the very beginning here, you would have seen like a whole bunch of variables being declared, including median. But I kind of like to keep the variables close to where they're being used, so you're not jumping back and forth trying to figure out what's going on. All right. So I think we're hopefully done now with our second step of writing this compute median function. And now it's time for us to go ahead and recompile and see if this works. Saving. Looks like we have all kinds of errors. Oh boy. I'm going to have to show this to you guys because, it's part of the fun of programming in C++ is getting horrible error messages. This is actually the kind of error message that my PhD thesis was trying to solve. And you'll notice that this has something to do with sort. Okay? Something went wrong with sort. And you don't really want to, you can sometimes glean some information from here, but there's something about assignment to a read-only location. Okay? So let's go back up to where we're doing this sort business here. Now, this is something I said last week or so, but it's been a good week or so since I talked about it. But it turns out this sort function actually does an in-place sort. Okay? So, and it doesn't like that we're sort of saying, hey, you're not allowed to change homework. We declared it as a const thing, right? Because we said, oh, we're not really changing homework, but then, that was actually wrong. We are changing it because of this sort thing. Now, at this point, we need to make a decision. Do we want our compute median function to sort of mutate its input for the sake of sorting or not? If you see this function called compute median and you give it some data, would you expect it to change the data or not? Probably not. So maybe what we want to do is we want to make the fact that we're mutating this vector is really sort of a internal kind of thing. Right, so maybe what we should do is create our own internal thing called homework. Let's change the name of this guy to HW. And we're going to copy that in. Or actually, you know what, even better? Let's go back to this original suggestion, which is to do it by value. Okay? So now by value, now it's making a copy, and then changes internally are not going to be reflected externally. Okay? Now we might we had a good reason for not doing it by value. We had this sort of generic reason of, hey, this is going to cost O of n. So do we have this scalability problem, right? But then again, let's look at, well, how much does sort cost? I don't know if you guys have had data structures or algorithms, but sorting is typically n log n, okay? O of n log n. So the sorting's already sort of fairly expensive. And so if you take O of n log n and then add it to something that's O of n, your overall time complexity is still O of n log n. So it doesn't really change the overall time complexity. So in this point, at least from a scalability point of view, we don't have to worry too much about, doing this more detailed analysis, we don't have to worry too much about the cost of the copy. And it sort of has the software engineering purpose that we like, that it's like, oh, you don't, when you call this compute median function, you don't have to worry about it, mutating something that seems like it should be read-only. All right, so we've done that. Let's try to do this again. Hey, that worked. Okay, now we can run it. This may seem sort of tedious to keep running things, but it's totally worth it. And in fact, if you were doing a larger system, what you'd want to do is you wouldn't keep rerunning these things by hand. Instead, what you'd have is you'd actually have a whole bunch of tests, like with different grades and things, and you'd have expected outputs for each of those, and you'd write a little shell script or something that would audit. You just push a button, it would say, yes, your program has passed the 100 tests that you've written for it. Okay, and that's called regression testing. But here we've sort of done our single test by hand, and it seems to be working okay. Again, having a much more sophisticated and larger number of tests would give me much more assurance than just running the one test. But already running one test is a lot better than none at all. Okay, great. So we've done the homework. And then let's just do, well, maybe we'll leave it at that for now, in that we've got just the one homework type. The last step that we could do is to wrap this part, or at least just this computation here, in a function called compute grade. But it's pretty much going to be this similar kind of process that we just went through, creating a function name, calling that function, figuring out what variables need to be passed as parameters or returned, and so on. Okay. Let's stop for a moment. The next step I'm going to do is talk about how do we extend this to multiple students, not just one student, but to be able to deal with a whole batch of students. But before that, maybe I'll pause for a second, and if you have any questions about this process of refactoring and creating functions.
You called it refactoring. Is that just subdividing into subprograms?
Not necessarily. So I'd say one of the most common kinds of refactoring is doing the subdividing. And this is very much task-based. So people would call this sort of procedural programming, of saying, okay, what tasks do I need to do? Let's make a function for each one of those things, or a procedure for each one of these things. Refactoring is a more broad term that encompasses other kinds of refactoring as well. So, and you'll see some things that do that in a moment. But you could also change how you work with your data, and that can be refactoring. Like you might want to group pieces of data together. For example, there's a whole bunch of data here that's sort of specific to a student. Okay, and it's sort of scattered around this program. There's the midterm and a final, and then there's this homework vector. And that's all for one student. Well, what if we have lots of students? Are we going to want, let's say you have 20 students. Are we going to want to have 3 variables times 20 is 60 variables to deal with our 20 students? No, that doesn't sound like such a good idea. So how can we organize our data differently to sort of deal with and not just 20 students, but what if we wanted to deal with an arbitrary number of students? with these online courses, you could have 100,000 students, right?
Okay.
Have we seen any data structures already that let us deal with arbitrary numbers of things?
Yeah, the structures, right, that let you call within a vector of things.
Yeah, so we want a vector. The vector data structure, lets you deal with arbitrary number of things. Like, so right now, per student, the number of homeworks can be who knows what, right? And so a vector will just be as big as it needs to be, right? Because we just keep pushing on the back of it, right? So we could do the same thing, but instead of just for homeworks, we could imagine a vector of student information things, okay? But we need to group together all the data for a student so that we can then stick it in a vector. Well, technically we could, for example, do 3 vectors, all the midterms, all the finals, and all the homeworks, but that's not as nice an organization. You'd rather have all the things for a student clustered together. So here is...
Full dimension vector?
Yeah, that's kind of what we want. And one way to do that is with what we call a struct. Okay, so this is a way of grouping data together. Let's call it student info. And then what you put inside of a struct here are, they look a lot like variable declarations. Okay, so we're going to have double median. Oh wait, no, not. Do we want? Is that one of them? No. We want the midterm. It's a different M word. Final, and then vector double homework. Okay. So these look like variable declarations, but really what you should think of it as that when student info now is a new type. You can now declare a variable as being a student info guy, right? So I could say, student info, Joe's info, right? That would declare a new variable called Joe's info, and then I could write down, if I wanted to, I could say Joe's info midterm dot midterm, and that accesses the part of the struct, okay? And then you can either read from it or assign to it. Now, at the moment, there's nothing in it, so I might, assign to it 100, right? And then Joe's info dot final, equals 90. And so now I'm assigning things into those. And then later on, I could access those out by saying, Joe info dot final.
So that looks really nice for usability, but in terms of internally and efficiency, it also runs fairly quickly?
Yeah. There's really not that much of a difference between having something in a struct versus having it as a local variable. Okay. Notice I said that much of a difference. If you really start, counting instructions and worrying about, the tiniest differences in performance, sometimes there is a difference. And it might depend on your compiler, actually. So some compilers are good at removing the difference, and some aren't. Okay, there's something called lightweight object optimization, or it's oftentimes called something about aggregates. Aggregate's another name for a struct, and there's this optimization that sort of pulls those apart. But we don't have to worry about those details for now. So we've got our student info struct. And now we can start to think about what we do down here. Well, now we're going to need a vector of student infos, right? I'll just call this students. Not indented properly. Horrendous. We'll leave it at that for now. Okay, so now we've got our vector of students. We've got a struct. Now we need to, instead of just doing this once, the entering of the grades, now we need to do it for every student. Okay, so we're going to need to put this in a loop. Though let's be a little bit more. Actually, no, we're getting a little short on time. So what I think I'll do is I'm going to pop over to the version that I already wrote up, and we'll see what we did there. So here's our students vector that we just created. And then what you'll see what I've done is I've taken all of that code for reading in a particular student, and I've created a new function called read, whose job is to read up all the information for one student. Let's pop up to see what that looks like, right? So it's pretty similar to what I did in the past, that we've pulled out that functionality and put it in here. I've gotten rid of the prompting. Okay, so the idea here is that no longer are we assuming that the person typing in this data is going to be like saying, oh, please type in the final exam grade. Okay, instead, it's more likely that we're going to be given a file of like a whole bunch of students and all their grades with the student name and then their midterm and final and then their homeworks, all just numbers on a line, maybe space separated. Okay, and so what's going on here is that we're just go ahead and we're reading in their name, the midterm and the final, and then the homeworks, right? So here's this pretty much the same function as before about reading in the homework. The previous version of that returned void. In other words, it didn't return anything. This time, I've changed it a little bit so that it's returning an iStream, so that we can signal like if you're done reading in stuff. Okay, and so if you can see with this version of homework, it's going to check to begin with if the in-stream is already in an error state, that means you're done. So let's not try to read any more in. So that's what that if is there. And then it goes ahead and tries to read in the homework, and that's about it. And it's going to put it directly into that member of the struct. Okay? So that's the read. So what will happen is when the read is done, it'll return an in-stream object that's sort of in an error state, and that'll signal for us to exit this loop. And then in the loop, the main thing we're doing is we're just adding each of those students to the students vector. Okay? And this may seem a little bit funny, but we're reusing this one variable student for sort of all the students. We're temporarily reading it into that struct and then copying that struct into the vector. So one thing you should know about pushback is it always does a copy, right? And if when it's just like a double or something, you don't even really think about it. But now it's doing a copy of the entire struct, okay? Which is important because what happens is during this read, we change that student. And so if it wasn't a copy, we'd end up with like a vector with all kinds of references back to one student, which is not what we want. Okay. Though to really get that, I would have had to do something like, I would have had to make this like a reference or a pointer or something. Okay. All right, the other thing we're doing here is we're saying, at the end of the day, we're going to want to print out a table with the student names in one column and their grades in another column. And so here we're keeping track of what was the longest name, so we know how big to make the column. Okay, so we're just computing the max length. And here what we're doing is we're starting out with max len at 0 here. And then what we're doing is we're just keep saying, what's the size of the name of the current student? And we'll take the bigger of the current max and that student. This max function is coming, again, from the standard library. Okay. In particular, I'm going to zoom up here. I've added a pound include actually, this pound include was already there for sort, but max is also coming from that same header file. Okay. Again, this is a place where, it's good to know sort of what's in the standard library. If you didn't realize that max was already there, there's a good chance you'd go and reinvent the wheel. Fortunately, max is a short function, so it's not a big deal, but it's good to avoid any typing that's unnecessary, and just go ahead and use that. All right. Now, what's coming up next is we want to print out this table of the students and their grades. And so what we're going to do here is alphabetize the students. Okay? And we're sorting the students based on their names. Okay, so this call to sort's a little bit different than what we've seen before. Normally, when you call sort, it uses like a less than operator. So it was using like less than on doubles to sort of sort the homeworks for the computing of the median. So now it's like, well, how do you compare two students? So what we're doing is we're giving a third argument that specifically says, how do you do it? And then up here is the function that I wrote. Okay, so here we're saying compare names. It's a function, takes two students in, S1 and S2. And what we're doing is we're saying, oh, well, let's use less than on their names. What do you think less than on? So the names are strings. What does less than on a string do? Does anyone have a guess or actually know?
There's the ASCII codes of the characters, maybe?
Yeah, but there's lots of them, right? I mean, there's like, it could be a 10
right.
ASCII, 10-letter word. So how do you compare two words?
Must be the first.
What's that?
Must be the first.
What do you mean by the first?
The first letter is, actually, I don't know.
So what if you had like one word that's like AB and the other word's BA? How do you decide which one comes first?
Use one as the most significant.
Yeah, right. And that's dictionary order. Or the fancy name for dictionary order is lexicographical. Okay? But dictionary order is, in fact, it turns out that the less than operator that's already provided for you by the string class does lexicographical ordering. Okay? Which is typically what you'd want, right? So we've sorted the students. Then we enter a loop that's going to print out the table. The first thing we do is print out the name, and we're making sure to use a certain number of characters to do that. And this set W is a special thing provided by the IOStream library that sets the width of sort of the number of characters you're going to use to print out something. And here we're taking the max len plus 1. We needed another pound include for set W. That's this IO manip. So there's all these things called manipulators that sort of change the way streams work. So this is one of them. Okay. And you'll see in a second what that looks like in terms of how it typesets or spaces out the name. Okay, then we actually compute the grade. Okay. So here we've got a new function for computing the grade. Here we're just passing in a student, right? So we're accessing the ith student from this array, from this vector, okay? And we're passing it to this grade function. And all this grade function, so here it is, we're passing in the struct S, and then in this version I had already created a grade program that took just the individual pieces. Where is that? I think that's up here, right? So here's the grade function with all the individual pieces, and this other grade function is just packaging it up. You'll notice that sort of this grade function is nicer in that there's only one parameter. So this is one of the benefits of putting things in structs and grouping things together, is it oftentimes reduces the clutter in your program. Having to think about 3 parameters is harder than saying, oh, I just need to put a student info in there and I'm good. So that's one of the benefits of sort of moving towards an object-oriented style of programming. What else do I want to say about this? It might seem unusual that now we have 2 functions with the same name, grade. How do we know whether, like this call to grade here, should it be calling this version or the other one? Okay, so being able to have multiple functions with the same name is called function overloading. Okay? And there's a fairly involved process that the compiler goes through to figure out which function to call. But I can give you sort of a really basic version of that process. So the first thing it's going to be looking at is numbers of parameters, right? And so, here you're passing in 3 parameters. You certainly can't be calling a 1-parameter function with 3 parameters, right? So that's one way it knows that you're really calling the other function. So you can also sometimes have the same number of parameters, but then you can, based on the types. So let's say we had a grade for student info, but then we also had another, maybe double grade for, employee info. Okay. Well, then what it'll do is it might look at the arguments that you're passing in, and it's like, oh, if it's the student info, then you're calling the student info one. If you're passing in employee info, because it knows the type of those variables that you're passing in, or the expression, then it'll call the other one. So it'll use the types of the arguments to figure out which function it should be calling. And indeed, there are places where it can be ambiguous, and then you really have a problem. But
So I guess I was thinking, why would you do that in a program? Why would you really want to have the same name?
good question. And it's actually a fairly common thought in programming language circles that function overloading is bad or evil. I actually personally disagree. I think it's great. And the reason why it's great is that our languages should help us humans. And we, as humans, we use overloading all the time. For example, if you see a cat walking down the street, would you want to say walk, or would you have to come up with some other term for when a cat does a walk versus a human does a walk? If it's kind of the same thing, you want to use the same name for it, right? So the same applies to programming. You're going to use those verbs for like compute median or compute grade. You're going to use these verbs to describe your functions. Why would you want to always be like making those things longer by like, you'd have to add on something like student grade here. And it's just sort of redundant information, right? So I think function overloading is good. And most of the time it doesn't cause problems. And it just helps the readability of the code. Good question. Any other questions about that? No? All right. So maybe I should, getting back to this sorting, we're passing in compare names. This might seem a little bit odd to you at first. It's like we're passing in a function to another function, okay? You'll sometimes hear the term higher order. A higher order function is a function that takes another function as a parameter. So sort here is a higher order function, okay? And it's just using higher order functions are a good way of making functions more flexible, right? This is a very flexible sort function because you can tell it how to do the comparison. And let's say instead of being sort of lowest to highest alphabetically dictionary order, what if you wanted it reversed? Well, that would be really easy. We just change this less than to a greater than. Or what if instead of sorting by name, let's say each student had an ID number. You could very easily change it to be using the ID number instead of the name. Okay. All right, so that's that. Okay, we talked about computing the grade. And then at the end here, we're just printing out the course grade, again setting the precision to 3 significant digits of the grade. And that's it. Again, we have this all wrapped up in a try and a catch because, for example, the grade function here might throw an exception. Okay. All right, so that's about it of what I wanted to cover today. Though we covered a fair bit of stuff today. Let's maybe do a recap. So we talked about refactoring and how do you break up pieces of your program into tasks and then make a function for every one of those tasks. That's a really important idea. One thing I want to stress is that you need to come up with a good name for each task. If you can't come up with a good name that matches exactly what happens in that function, then there's something wrong. Maybe you're trying to put too many things into that function. Like if you have the urge to use the word "and" in a function name, stop and maybe pull that one function into two functions or something like that. Okay, it's always, it's tempting, but it's sort of the road to pain and suffering to put more than one thing in a function. One conceptual thing. Okay, we also looked at dealing with refactoring data. So up here, we defined a struct. There it is, for grouping together a bunch of variables. And that facilitated us being able to put that struct, lots of copies of that struct, into a vector to be able to deal with any number of students. Okay? And then you saw some function overloading. And here, this is quite nice. You'll often see, for student infos, you might think to yourself, well, what can I do with a student info? Right? And you might actually have a number of functions that all take student infos as their parameter. And you can think of these as like the verbs or the actions that you do with the student info. Here, we just have one, which is grade. Compute the grade for student info. But as this program gets bigger, you might have other things that you might want to do with the student info. And you'd then decide to create more functions like this. Okay? And then maybe the last point I want to go over again is that this notion of being able to create a function like compare names and pass it into another function like sort. Okay. And lots of the standard library algorithms are higher order, and then usually it's optional. So there might be some meaningful default like use less than, but then if you want to do something special, then you can pass in your own function. All right. Any last questions for today? Yeah.
Question. Is there any way we can have a copy of the code?
Sure. I can. Maybe what I'll do is on my web page, I'll post a copy of all the code we've gone through so far.
Awesome.
Yep.
Thank you.
All right. Thanks a lot.